Oh, 1820. Okay, so for senior history.
Well, there you go. I will begin with a word of prayer. I think everybody who's here is here. So, Heavenly Father, we thank you for this day. We thank you for your resurrection, that we can serve a living God. We pray that you be with us today. Help us to glorify you, what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so I was warned there are mistakes in my solution to mission 3. Let me see if I can find them. I learned this news about 20 minutes ago, so it's supposedly reflected in the grading. I forgot which one he said. I'm assuming it's one of the ones I had him grade. Oh yeah, so problem 108. He's the grader says there's a couple mistakes in my solution, and let's see here what else. Well, I'll have to look back at his email and let you know later. But yeah, it was problem 108 that there was a mistake. Basically, I jumped. So I go from like the coefficient being alpha minus 1, and I somehow changed it to, I jumped like minus 1/2 if you look at the 4th line down in my solution. But anyway, so like the coefficients of the x to the 8th and the x to the 12th in problem 108 are currently incorrect, but I'll make an announcement about this later, okay guys? I just wanted to tell you now. So any questions about anything before I get started? I know, obviously you're like, why haven't you top hatted yet? I have been thirsting for top hat these many days that I've been away from Liberty. My life is not complete without the top hatting. I hear you. I'll fix it. Give me a second. You know, it's not that you want top hat, you need it.
It costs us like $50. $50. Right?
That's money you already spent.
Yeah,
you know?
What if we can alleviate?
It's like a dowry already paid.
Yes, but what if we can alleviate the refreshment of paying that dowry?
You want to divorce this wife and no?
We want to keep that.
Well, from the if it was within my power, I would let you, from the hardness of your heart, divorce Top Hat. But sadly, it's not in my power. So, guys, I will eventually do the silly Top Hat once my computer comes to life. So I've started down a path which is talking about what I would call the infinitesimal method. Do you guys know what the infinitesimal method is? The method of infinitesimals. Sounds like a safe answer. Let's see here. But so I would say, roughly speaking, it's a principle of mathematical modeling. It's a heuristic principle. Essentially, the idea is this: is if you can sort of sketch out how a given problem works at the infinitesimal level, then you can integrate it to find the total result. So like I did this, I think last time for center of mass. You know, I indicated how we would find the center of mass of like a wire by looking at the continuous extension of the center of mass formula. And I didn't finish that integration, but I hope that's okay with you guys. Let's see here. All right. So let me just give you some examples of this method. So like the first, maybe the foundational one for us, right, is if you're thinking about, you know, an area, right? And you slice it like so, what can you say? What's this? The thickness, right, is dx, and the height is what? F of x, yeah? So what's the little bit of area? A little bit of area here, f of x dx, right? So to find the total area, what do? Integrate from a to b f of x dx, right? So that's one example of what I would call the infinitesimal method. Another example, if my area looks something like, oh, I don't know, like that, perhaps, all right? And so I'm going from, say, here, A, and up here to B. And I've got a clear, you know, a clearly defined left and right. So like, say this is XR, and this over here is the left X, XL. I can chop that area into a bunch of slices, right? I can chop it into a bunch of horizontal slices like so. And I can think about, well, the thickness of this is what? It's dy, right? What's the little bit of area here for the strip? It's what? It's the right x minus the left x times, this time, dy. So what's my total area here in this case? I would have what? I would have a integral from a to b of the right x minus the left x dy, right? Now here, the right and the left x are both what? They're both functions of y, right? And so you wouldn't want to do example 2 the way you did example 1, because it's just not a reasonable problem for functions, right? Fails the vertical line test on the edges, right? If you were going to look at this as a sum of vertically sliced areas, you'd have to break into a bunch of cases. It'd be a pain. All right, what's another example of the infinitesimal method? Well, another example is, you know, when we have a, you know, something like, oh, I don't know, some sort of, you know, solid, like this, let's say, and you want to calculate the volume, right? So what do? You slice it, right? You chop it into a bunch of slices, something like this, perhaps, right? And so if this direction is z, let's say, then the thickness would be dz. And if you can talk about here, like let's call this the radius, then what's the volume? Well, the volume of this this washer, right, is just pi times the radius squared times dz, right? And whatever this, you know, I've drawn it like it's a sphere, right? So you know what to do. You just, but you know, let's make it more interesting. Let's make it like a, I don't know, some kind of weird looking thing like that, right? Yeah. But what I mean here though is that in order for this to make sense, at each point need our function of z alone, right? If that's the case though, and this down here is like z naught, and up here is z1, then the volume would be the integral from z naught to z1 of pi r squared dz, right? You just add up the volume of each slice all the way, right? Can you guys tell me any other examples of the infinitesimal method? What's the other thing you can do with the volume? We could slice it into cylindrical shells, right? And add the volume of each shell up by integrating. Yep.
And this is that we learned last semester.
Yes, we learned this last semester, hopefully. But now we're adding to this list, right? Because now we also can talk about, you know, example 4, you can have a curve, right? And you can talk about calculating its arc length. How do you do it? Well, basically, you just take a little stretch of it. You call it a ds, right? And you look at the part that's dx, the part that's dy. ds squared is dx squared plus dy squared, right? Well, square rooted. And then use your imagination a little bit. That's the square root of dx dt squared plus dy dt squared dt, right? And if this is, say, t equals to a, and this is where you've got t equals to b, then the arc length is what? Integral from a to b of this. But it's yet again another example of the infinitesimal method. The infinitesimal method is with us everywhere in our applications of integral calculus. Basically, we're always thinking about how to set it up in the small so we can integrate to get to the large. All right? Another example from physics. If you have work is what? Work is equal to force times distance, right? But when does this formula make sense? It really only makes sense if the force is the same over the whole distance, right? Otherwise, the question is which force? The force at the beginning, the force at the middle, the force at the end. But think about this. If you talk about the infinitesimal work done by a force over an infinitesimal distance dx, then the question of which force goes away, because the force is essentially the same as you go over the displacement dx. Yeah.
With the ds squared, this would be ds, since you have to square it over.
Oh, yeah, thank you. So again, this is the little bit of work done by the force over the little displacement dx, right? And to find the total work done, one-dimensional motion, of course, we integrate, right? x1 to x2, f of x, f dx, right? Now this formula, of course, is limited to one-dimensional motion, and if you're in my physics class, you've experienced what happens elsewhere. But what happens elsewhere requires calculus 3. Just like back here in example 3, if r is not a function of z alone, also calculus 3, because basically this strategy of making everything a one-dimensional integral only works for solids that are sufficiently symmetric as to permit a uniform concept of like radius or some kind of regular estimate of the size of the cross-sectional slice as a function of the coordinate along the axis. And that's a pretty special set of volumes, right? Most volumes are more lumpy than that, you know? Right? Okay, so example 6. And so finally, here's the new one, all right? Suppose you want to calculate surface area. What's surface area? So you might have something like I don't know, I'm not good at these pictures, but so something like this, some kind of surface of revolution. How would you calculate the area of such a surface? Well, what you do is you chop it into ribbons, right? So like, if I think about it, well, the easiest ribbon to draw is the one on the edge here, right? Like this one. So what's the area of this one band, right? What would the area of this one be over here, you know? See, we'd like to say what's the little, we'll use a capital S for surface area. How should I, what do I need to know in order to figure that out? Well, how about this? Essentially, the idea is this. If you were to, excuse me, look at this length here, what would this length be? What's this length here? It's not dx or dy, right? Because when the surface is more slanted or less slanted, it depends, that changes the our idea of what the ribbon's area should be. What we want to use there is ds, little ds, right? Little ds. And how, if you were to just take, let me make it green. If you were to take the green ribbon and just lay it flat, how long would the ribbon be? I'm trying to convince you that the width of the ribbon is ds, right? But how long would this ribbon be if I laid it flat? Just cut it, and lay it flat. How long is it? The circumference, right? And how would we get that? R, so where this distance is here, right? I agree. I think that's what we want, 2 pi r, whatever that is. All right? And so the little bit of surface area then from that one ribbon would be 2 pi r ds. But what does that mean? How would you calculate that? Well, that depends on how we were describing the surface, right? But I'm talking about this surface as if it's a surface of revolution. How do you get a surface of revolution? We've looked at these in the previous course, right? So there's various ways you could do it. One way, kind of the most boring way, would be if you think about the top profile of this curve, of this shape here, like this one. Oh man, let's make it red. So this top red profile curve here. Unintentional, of course. Let's see here, y, if that was y equals f of x, right? And then you're taking that y equals f of x curve and you're rotating it around the x-axis, right? That's one way we could form the surface of revolution. In that case, what would ds be? So essentially, if you have y equals f of x, you can think of this in some sense as x equals to t and y equals to f of t, right? It's the case we're parametrizing the curve by using x as the parameter, right? So in this context, what's ds look like? Well, what's r, for one thing? R is y, right? So I'm going to write this in terms of x and y for a second here. So you got 2 pi y times the square root of 1 plus dy dx quantity squared dx. So this is what the formula for arc length would look like in terms of a graph. Not arc length, surface area, right? Surface area. How would this look like if we were instead to use a parametric description of the profile curve? Instead of looking at x as a parameter, we look at t as a parameter. The formula would be a little bit different, right? It would still be y there, right? Where y is understood to be a function of time. But now you'd have dx dt plus dy dt dt, right? So this is the formula you would integrate if it was a graph of a function. The second one's the formula you integrate if you had a parametric curve you're rotating to find the surface area, right? What if instead of rotating around the x-axis, you're rotating around the y-axis? Then you'd have to swap out your radius for a new, like for x instead of y, right? Like if you're rotating around the y-axis, then this y out front would become an x, you know? And you could think about other weirder stuff, right? Like rotating a surface around like some other axis, like x equals 2. Then you'd be like looking for the difference between 2 and your surface as the radial distance. So you have to think, like this top equation has many, many geometric applications, right? These are special cases, all right? I don't think your homework delves too deeply into how to set up formulas for different axes. I'm just saying that's something to think about, right? So should we work? Let's work an example with numbers. You won't be surprised by my example, I don't think. How about if we do the sphere? How would we obtain the sphere? How to obtain sphere radius r as surface of revolution, how would you do it? Let me get you started. So I would think about the xy axis, right? I'll do it like that. What profile curve do I want to get a sphere rotated around the x-axis? Semicircle, right. And as you think about your life and about what we're going to integrate, what do you want to do? Graph or parametrization? I would strongly recommend parametrization, yes. So parametrically, what we're looking at here is x equals to r cos t and y equals to r sine t. At least that's a good choice. And if I want just the top half, what do I want? This here is what? This is t equals to 0 for those formulas, right? And over here is t equals to pi for those formulas, because if you plug in t equal to 0, you get x equals to r, y equals to 0. If you plug in x equals to t equal to pi, you get x equals to minus r, y equals to 0. So, great. What's the x dt squared plus dy dt squared here? So, by the way, I like this notation for problems. What's x dot? What's y dot? That saves me some writing, you know? X dot is dx dt, y dot is dy dt, right? X dot here is minus r sine t, and y dot is r cosine t. So what is x dot squared plus y dot squared? So we've got minus r sine t quantity squared, r cosine t quantity squared. What's that give us? There's no negative. The minus gets squashed in the squaring. There's an r squared, right? And what else is, then you have r squared, that factors out. You've got sine squared plus cosine squared, which is 2. How dare you? I'd expect that from Sasser, but let's see here.
Man, I'm just taking my notes.
Yeah. I'm not saying that you'd say that from a misunderstanding. I'm saying that you'd say that as a point of harassment.
Oh.
But I realize that I probably should be, it's probably ham that I should be worried about. See, anyway, so r squared is the speed squared, right? X dot squared plus y dot squared. This is speed squared. So this is literally ds dt quantity squared. Anyway, so what's the point of all this? Well, I've worked out that ds is in fact equal to r dt for this circle curve. Because the thing inside the square root for the arc length, right, infinitesimal if you will, ds is the arc length infinitesimal. It's just r dt. So what's my d big S here? 2 pi y ds, right? Little ds. What's my y? R sine t, right? So we get 2 pi r sine t. What's my ds? My ds is r dt. And so what's our concept here? We're slicing the sphere into these ribbons, right? That happens for what t? From which t to which t? T equals 0 all the way over to what? T equals to pi, right? So our integration should happen over the same. So the total surface area then for the sphere is the integral from 0 to pi of 2 pi r squared sine t dt, which is 2 pi r squared minus cosine t. Evaluate that thing from 0 to pi, and out you get 4 pi r squared, because the integral of sine from 0 to pi is 2, actually. There you get minus cosine of pi minus a minus 1, which is 1 plus 1, which is 2. 2 times 2 is 4. 4 pi r squared, the well-known formula for the surface area of a sphere, right? So like, if I was going to put this on like test 4, maybe the way it would appear would just be this. Show the surface area of a sphere as 4 pi r squared. It's up to you to provide the formulas that parametrize the circle and to put this story together, right? Yeah.
So what's the purpose in like parametrizing?
What's the purpose in parametrizing?
Yeah.
Well, I don't know. It's like asking, why would you want to have a, oh man, I've forgotten the name for this stupid thing. So I used to only have one kind of drill. I used to have like the linear torque drill. We've had these forever. They're just a motor attached to a thing that turns, right? They're dumb. They just, you press the button and they go, right? And I built the playground with it. I put in thousands of screws, thousands, right? And at the end of that, a friend of mine is like, do you have a such and so forth? I've forgotten the name of this stupid thing, but it's got variable torque. You ever heard these drills that go brrr? What's it called? Impact. Yes, an impact driver. I didn't have an impact driver. Now, does the impact driver do anything screwdriver doesn't do? Not really. I mean, they both just put in screws, right? But which is better? The impact driver is better. It's a much better tool. Your wrists will not hurt after you put in a thousand screws. It'll just be like another day, you know? And the same with functions. Functions are like the linear drill. You've known about them. They're wonderful. They work when they work. They're inexpensive. We sell them to you in pre-calculus, even college algebra. But there's many jobs they're not suited for. And the same with parametric functions. It's like, it's answering the same set of questions, but the difference is with the parametrization is it doesn't care which is x and which is y, right? They're both on the same level ground. So any curve which has some kind of symmetry between x and y, it's probably better suited with parametrization, with a parametric viewpoint, because it doesn't single out y as if it's special. If I single out y as if it's special, the formulas I have to deal with here are y equals the square root of r squared minus x squared, yeah? And so if I chase that rabbit and I calculate the surface area with this formula over here, then I have to differentiate that, right? I have to differentiate that. Now, could you do it? Sure, you could do it. It wouldn't even be that bad, probably. Probably. But this is so much easier.
So with the parameterization, you're able to get the x and the y like in terms of the same variable?
X and y in terms of the same there. What's your question again?
Like with parameterization, you're able to get x and y like in terms like of t.
Oh, yes, yes,
so
x.
like, makes it more simple.
I think so. I mean, it's, in some sense, using parametrization for a curve, it kind of, in some sense, lays down an axis in the direction of the curve. And that makes things, could make things more simple. This is sort of it. I don't know. Yeah.
How'd you get the ds is equal to rdt? Is that from?
Oh, see, one of the fundamental truths that we hold to is this, that ds dt. And so I haven't said this yet, but that's a good question, Luke. So, you know, ds dt, well, let me say this. S at time t, we could actually get from the integral from, say, a base time t naught to t of the square root of, let us say, dx d tau squared plus dy d tau squared d tau. So this is the arc length function. as a function of time, right? What happens when you differentiate that with respect to time? Differentiate that formula with respect to time t. What do you get? ds dt is what? Well, fundamental theorem of calculus part 1 says it's the integrand, where you replace the integration variable tau with time t. But what is that? This square root of dx dt squared plus dy dt squared. What is that? This is what we call the speed, right? That's the magnitude of the velocity vector. You know, that's the length of the vector dx dt, dy dt. In other words, the speed is ds dt if you want to think about it in terms of physics. But the larger point here is that the infinitesimal change of the arc length with respect to the parameter, in other words, ds dt, is given by the square root of dx dt squared plus dy dt squared. So if I multiply that equation by dt, I get this formula, which I'll write here so everybody can see it, ds square root. So I would refer to this as the infinitesimal arc length formula, if you like. Admittedly, that's a somewhat heuristic idea, but I find it, I mean, it's more than just well, it's a mnemonic, it's a guiding principle. I'm not sure I've actually answered your question, but these are things I wanted to say.
So you're saying that the square root of dx dt squared plus dy dt squared is equal to r? You're saying?
I'm saying for the circle, dx dt squared plus dy dt squared is equal to r squared by this calculation right here. So this is dx dt squared plus dy dt squared. Gives you r squared sine squared plus cosine squared, which is just r squared. And so when I take the square root of this, right, I get r is equal to ds dt, which then I solve for ds, basically. So that was actually your question, but I wanted to chase a rabbit. Well, actually, that's not really a rabbit. I mean, there is something that's easy enough to believe if people tell you it, but there's something to prove there. Like, why is it that the magnitude of the velocity is the infinitesimal change of arc length with respect to time? I mean, there is something to prove there. It is true. The proof is right there. But when is the arc length defined for a curve? What would you need? Think about this for a second. You need for it to be sort of what we'd expect it to be, you need the curve to have speed non-zero, right? As long as the speed is non-zero, you can count on the arc length increasing, right? If you did have a path, right, where the parametrization did like this, right? Whoop. Right, that would mess you up, right? If you have a place where your parametrization just stops inadvertently, that's going to mess up like what you'd naturally conceive for the properties of the arc length function, namely that it's like strictly increasing as you go along the curve. So for the nicest arc length functions, it's important to assume that the parametrization of your curve is what's called nonstop, right? I have not beset you guys with, blathering about how to make sure the parametrization is nice. But there are things to think about there. There's a curve. Check this out. There's a curve whose image is the unit square. The curve literally fills in every single point in the unit square. This is called a space-filling curve. Now you might wonder how you do such a thing. The answer is you're a 19th century mathematician with too much time on their hands, right? Pretty much. Well, I can do it. I can show you Desmos here. Let's do it. Yes, sir.
How do you choose what to make your parameters?
How do you choose what to make your parameters is an excellent question. And I think the best, let me come back to your question just a second. So that's pretty much all I have to say about the infinitesimal method, all right? I wanted to show you that we can set up these formulas by a guiding principle. Like, I don't have to look up in a calculus book what's the formula for calculating arc length. What's the formula for calculating surface area? What's the formula for calculating area in different ways? Because I can set it up from the infinitesimal method. It's a guiding principle that will, you know, and it will also help me create new models and new integrals where there wasn't one even known before. Yeah? Which is something you might need to do as an engineer if you create something and you need to work out the math for it from base principles, but somebody hasn't already written it in a book for you. You know? So, I mean, some of you want to be like master engineers, right? So it's the kind of thing you ought to be able to do. Let's see here. Come on. Or maybe you want to go to physics graduate school, where it's also the kind of thing you might be forced to do. Well, wake up. Come back to us. So your question was, how do you find the parametrization? And so, like, we need something to chew on. Like, what's an example that you have in mind?
Oh, I have no idea.
No idea? Well, here's one. Man, what example am I on here? Example 8. All right, so let's face something here. How about x squared plus 4x plus 3y squared equals to 0. You want to parametrize this thing. All right. And you'd like to parametrize it in a counterclockwise sense, let's say, if that makes sense. I don't know if it makes sense or not. So what I would do with something like this is I go, well, I could solve for y, right? But that wouldn't be particularly elegant or interesting. So what I would do for something like this is I would complete the square. I have x plus 2 quantity squared, right? Minus 4 plus 3y squared equal to 0, which gives me x plus 2 quantity squared plus 3y squared equals to 4. So my opening move is if there's some way to make it more algebraically like lucid, to make it fit some pattern I'm comfortable with, I do that. So sometimes completing the square is the right thing. See, at this point, it looks like a circle, kinda, right? But there's that what? What's cramping our style? This 3 here, right? But if this, okay, so what I'm thinking here at this point is something like, if I could make this 2 cosine t squared, right? And if I could make this 2 sine t squared, then I would at least get 4, right? So I see, okay, well, if I can do that, so that says to me, oh, what I should do is I should make x plus 2 equal to 2 cosine t. And if I make, 3y equal to, oh, wait a minute, not 3y, square root of 3y, right? And you make the square root of 3y equal to 2 sine t. In other words, parametric equations, minus 2 plus 2 cosine t, and y equals to 2 over the square root of 3 sine t. Well, that should work out pretty nicely here. For this, what is this?
It's an ellipse.
It is an ellipse, right?
Over 2 on the x-axis.
Yeah, so precisely. Now, I think not everybody here is good on that. Like, some of you would benefit from me spending about an hour just to talk about conic sections, right? We should do that. Maybe tomorrow. So this is an ellipse. Centered, minus 2, 0. Come on. Forgot to plug this thing in. If I plug it in, it'll stop turning off on us. Now, suppose you don't have a sort of an epiphany that, oh, I need to complete the square, right? So if I'm looking for this kind of answer for the parametrization from you guys, I do try to do something to sort of direct your activity in that way, you know. But the thing is, there are other ways to parameterize that curve, like no doubt. For example, you can just solve for y, right? Y is equal to plus or minus the square root of, you know, apparently 1/3 minus x squared minus 4x. So that would then give you a parameterization. You could do what? You could do like x equals to t, y equals to, you got to pick one. Let's pick the positive one. So I much prefer the parameterization above to the parameterization below, because of, if I want to do anything, goodness gracious, the sine cosine parameterization is going to be so much easier to do calculations with, and also just to understand. Because, you know, if I do something like, I say at the start of this, I give you some sort of cryptic instructions like parameterize the, you know, the upper right corner of this curve. That would be more, well, I guess you could still achieve it with this, but if I wanted to parameterize just the upper right corner of this, right, I would just limit t to go from 0 to pi over 2. That would trace over the right and the upper half of the ellipse, because, well, let's look at it. So one of the things you guys should do is use Desmos, a little bit at least, to help you visualize these things. So check this out. If I do minus 2 plus 2 cosine t here, comma, what do we got? 2 sine t divided by square root of 3, is it? All right. So there's t0 to 1. If I do 2 pi, what happens? It goes all the way around, right? So there you go. That's the ellipse that we're talking about. Suppose you want to look at it. You want to see the evolution of time. Here's something you could do. It's pretty easy. Put a slider there. Let the slider pick the range to go, say, from 0 to, oh, I don't know, 6.3 I'll do. And I'll do it in steps of however big you want the steps to be. I'll 0.01 to make it kind of smooth. And I probably want to make the animation just go one way. So there you go. Now we're tracing out the ellipse, right? There's the evolution of time. You can, you know, that took me all of 3 seconds. I mean, if you'd like to use Mathematica and spend a couple hours figuring out how to do this, feel free. If you'd like to use MATLAB and spend a couple hours to figure out how to do this, by all means, feel free. Or you could just open up Desmos on anything and do this, right? Mathematica and MATLAB have their place, right? This is useless to an employer. If you want to provide something that's archival, that you can redo for arbitrary examples with more complicated data, this is not the tool to use, right? Although people do absurd things with Desmos. But, I forgot about the trouble. Oh, okay, so like, in this, I was thinking about this. So you guys got some problems about collisions and intersections, right? So what if we looked at, let me pause this here for a second. What if I do a circle, you know, of like, I don't know, radius 2 centered at the origin? That would be what? 2 cos t, let's say. 2 sine t. And we'll just, I mean, I'll show you to start with. If I go from 0 to, you know, well, if I go to 0 to 3, what's that going to be? Not quite a full circle, right? If I make there's a half circle, a semicircle, if I make my parameter 0 to pi. If I wanted 3/4 of a circle, I could do 3 pi over 2, like that. If I want it to go, well, let's see, let's look at let's make it go the same. Let's make it share the same time, if you will, as the other one. So here we go. Do they collide? No. Do they intersect? Yes. how could I adjust the parametrization for this circle to make it collide with the red one?
Shift the center over.
Oh, no, without moving the circle. How can I adjust the parametrization of the given circle to make it collide? Speed it up.
You could solve the distance between the 2 points.
Yeah, to make it collide, I need to well, yeah, we could either make it speed up or we could maybe shift the parameter so that's whatever time 0 is for the green curve, we would want to be whatever that time is. Let me make them intersect at a more convenient place. Where do they intersect, actually? How would you figure that out? So, by the way, I did post a parametrization guide in Canvas that has like a list of the most important formulas for conic sections. But I want to explain where those formulas come from. That's what takes me more time. To actually understand the formulas for the conic sections, that's pretty simple. You use cosine and sine for ellipses and circles. You use cosh and sinh for hyperbolas. That's pretty much it. And you need to complete the square to take mind of, I guess I have to do it, well, if I can remember the formula. X squared plus 4x plus 3y squared equals to 0. X squared plus 4x plus 3y squared equals to 0. I made it. I made it. What's the equation of the green circle? Equals to 4, right? So if I'm looking for intersection points, actually I don't like the parametric viewpoint. I like the Cartesian viewpoint. It's easier to find points of intersection. But I mean, let's see. So let me just do it in stages here. How do you solve this system? Oof. Solve for y squared. I like that. Y squared. 4 minus x squared, plug that into the other one. Then what do we have? We've got minus 2x squared plus 4x plus 12, also known as x squared minus 2x minus 6 equal to 0. If that actually factored, it would be amazing, because I just made this stuff up, you know. But I don't, I don't think this factors nicely, right? But we can complete the square. So this is x minus 1 squared minus 7 equals to 0. So x is equal to 1 plus or minus the square root of 7. Ooh. Yeah. Huh. Is that right? X equals to 1. That feels wrong. Oh, wait a minute. Square root of 7 is big, isn't it? So it's funny. It's funny how it gives you, that's obviously going to be like the 1 minus square root of 7 solution, right? It's just, it has an extraneous one over here. I don't know why that is. That's curious. Cool. So I'm pretty sure we want x equals to 1 minus the square root of 7 for our intersection point. If I haven't made a mistake, if I have, please chime in. And then what's my y? Well, actually, who cares, right? So my question then is, what time do both curves get here? Well, paths, I should say. So to find the time that the red curve reaches there, I should do what? So for the red curve, ellipse, right? I would set 1 minus the square root of 7 equal to, what was my formula?
Minus 2 plus 2.
Minus 2 plus 2 cosine t, right? And for the green circle, let's see here, x is what, 2 cosine t. Now these, of course, these are not going to be the same times, right? We already know that. We can see it. And so what is the solution here? We've got 2 cosine t, 3 minus root 7. So t inverse cosine of 3 minus root 7 over 2. So t is what? I guess we could try to work out the power series for inverse cosine and work it out by hand, right? But let me... now we need radians. So I'll take your 79.8, which I believe to be degrees. Am I right?
Yep.
Okay, and I will... 1.39 radians? Okay, yeah, these formulas are, the formulas that I wrote down are in terms of radian measure, okay? Because when we take a derivative of cosine and we get sine from either minus sign, we're using radians. If you're using degrees, you get multipliers by like 180 everywhere, because the sine in degrees and function and the sine in radian functions are technically different functions. That's why you have to change the thing on your calculator so it knows which one you're using. Right? They're geometrically identified, but they are actually different functions. They have different input output. Okay, so anyway, 1.39 for the ellipse. How about this one? Inverse cosine apparently of what? 1 minus root 7. What's that? What did you get? Or you got something? Ah. I'm in, let's see here. I get a 2.53, is that right? All right, so how much are they missing each other by? About 1.147 seconds, right? So here's a simple thing I can do. If I want to do what? Which one's getting there too late? The green one, right? So if I shift it by 1.15-ish, and see if you just do one, that's something else, isn't it? Oh man, that didn't work. Oh! So, you know, if you're like planning a heist or something, these are the kinds of things you need to engineer, right? So, I suppose there are legal applications as well, you know, correct planning.
How's this? Wait, how does? I don't want to know. Asking for the first round.
How is it? Oh, well, all of these heist movies involve some sort of like, you know, you got to make a diorama of the bank, and you know, you got to plot where the different things are, and you got your little matchbox cars, and you got to plan which is going where and all that, and you know, yeah, right place at the right time, that sort of thing. Actually, are they still making heist movies? I've lost track. Like I think there was a time where every third movie was made was a heist movie. You know.
They made a good heist show. You could watch
A heist show.
You could watch it in any order, like the episodes.
So, let's see here. Do you guys have any? Let me see if I can find. Anyway, I wanted to show you this because you really should be using Desmos to help yourself out if you're like stuck on a homework problem, because you can at least see what you're trying to do algebraically. It can help you, right? But I know it doesn't help you for the test, but you know, I do think there's things to be learned through these things that can, increase your understanding, your sort of basic intuition for how functions work and things like that. But, all right. And also the slider, I tell you what, the slider in mathematics, the slider in Desmos is just, it's so nice. When I was working for the Navy for that year, like everything's behind us, everything's behind, there's security, right? Security upon security upon security. So you can't just, sometimes there's places where you can't use this, all right? Because you can't just log on to the web there because you're in a vault with secure information. Like you can't just log on to the internet. At least you can't do it where you have the data that you'd like to use these things on. So like, I don't know, there were various places where I really would have benefited greatly from being able to like just put a slider and just like adjust things I was looking at with a slider, and I couldn't. So I don't know, if you could figure out how to build these things in MATLAB, that would be super useful for you if you find yourself working in a government lab sometime in the future. But where was I? Let me put this away. Actually, before I do that, let's look at the Yeah, so I won't do the unit square for you guys, but I will do something similar. So the thing that we're talking about next, once we get past parametric equations, and I've more or less told you what I have to tell you. Like the rest of it's an art. So we can talk about your specific homework problems if you're stuck on them, but that's kind of like the only thing I have left to do for you. I guess we can work some more examples, but past this is polar equations, right? So polar equations, polar coordinates, here's an interesting one. This is r equals to theta. This is, of course, a spiral, right? The radius is proportional to the angle. And it just keeps being bigger and bigger and bigger, right? Because for one angle, for example, the x-axis has angle 2 pi. Well, I guess the 0 here, and then angle 2 pi maybe? Yeah, 2 pi, 4 pi, 6 pi, 7 pi, 8 pi, and so forth, all right? Pi is about 3, so. And of course, you could do other interesting stuff, like, I don't know. So there's sine of a theta. And so you'll notice when we have like whole numbers, really nice stuff happens, right? Like here's the graph of sine of 2 theta. R equals sine 2 theta. It's a four petal rows or something, right? If I get to 3, how many petals do you think they're going to be? 6. I have a guess for 6. I have a guess for 3. Those seem like very good guesses. Who is the winner? 3. What if we go to 4? How many petals? I have a 4 and I have an 8. Who's going to be the winner? Looks like 8. So anyway, so if you have whole numbers, it's interesting because as we'll study in detail in a future class, the equation kind of like loops back on itself. It just keeps repeating the same pattern, right? But if on the other hand, A is not, if A is not a rational number, but it's like, off a bit, then it may take a long time for it to get back again. To really make this unpleasant, I need to put something here which is definitely irrational. What's a nice irrational number? I square root of 2? I'll go with the square root of 2. So you're like, well, it's kind of sort of okay. Okay, let's keep going on. Instead of just going to 12 pi, let's go to 100. It's never really going back where it started again. Let's go to 1,000. Let's go to 10,000.